thing done. Hello and welcome back to Calculus 1. We are starting chapter 5 on integration. So we're going to actually ease into it, starting from the middle school concept of an area of a rectangle. So if you haven't seen rectangle before, quit the class. This is the rectangle. It's a two-dimensional mathematical concept. You can draw this on a wall or on the floor. It's 2D, has a dimension of x and has a dimension of y. You can also call it a and b, and its area is simply x times y. So that's the area of the rectangle. So now if I want to put this in a coordinate system, I can. And I can, let's say, shoot a function over here, f of x equals to 2. That's known as a constant function. And then I can cut that function, let's say, here and here at 2 and 5. So if I do that, that will make this side to be 3 and this side to be 2. So area would be 3 times 2, which is 6 units squared. And if you carefully pay attention, you will see 1, 2, 3, 4, 5, 6 squares inside, and the area is 6. So you have 6 1-by-1 squares inside of this shape. So that's the preliminary stuff from your middle school that you should know to survive this lecture. Now we are moving to approximating area under the curve. So we've seen here, if the curve, i.e. function, if that's just a constant function going from whatever number to whatever number, you have a rectangle bounded by those 4 lines. One is x-axis, right? So we have x and y-axis there. So one is x-axis, one is the function on the top, and then 2 on the sides. That creates a rectangle, and you can calculate its area. But what do you do if the function is not constant? What do we do if we have a curve like this? Right, so this is now our function f of x, and what I'm going to do is I'm going to find the area from the 0, which is a, all the way to the other end, that is b. And the way I'm going to do this, 1, 2, 3, 4, 5, yeah, great. I'm going to cut with this vertical line in half. So find exactly where is half between a and b. And then find the half of each half. In our case, let's say here and let's say here. So what I have is I created, for simplicity, equal distance for these cuts, and I am going to label these x0, x1, x2, x3, and x4. Those 0, 1, 2, 3, 4, they're just counters, okay? We count so we know which location we are talking about, and we see that our x0 is our a, and our xn, which is the last one, is our b. And I'll just put last one. Why do I put n? Well, because I decided to cut now with 4 rectangles, which are 3 lines. But if I put more lines, there will be more rectangles, and then obviously that x to the x4 would be either x5 or x6 or x10, right, depending on how many of these you want. So I have to call the last one xn, because that depends on your choice, or obviously in my case, my problem that I put on the test, and then you call that one the last, which is b. All right, great. Now, obviously, these are not rectangles. These are, they are nothing because the one side is curved. All right. But what we are going to do is we are going to pick left hand rectangles. Now, when I say left-hand rectangle and I draw this point, I'll just point there and say f of x. That means that the left side of the top of the rectangle is touching the function. Left side. So I will have to draw my rectangles like this. So this is the way we would draw our left rectangles, because the left side is the one that is touching the function. Now we see that the area that we are getting is actually bigger than what we need, because everything that is poking out of the function is error. That's extra, right? And if we had scissors, we would just cut that off and throw it in the garbage, right? But see, the trick is that we are now trying to approximate area under the curve, and we can only deal with rectangles so far. So this is the best we can do for now. So what I'm going to do now is I'm going to create the formula. I am going to observe that this one over here is f of x0. Then this one over here is f of x1. Then this one over here is f of x2. The heights, and f of x3. So you can see that each one of these points is the height of the rectangle, meaning our y value. And we have the distance in between all of these, which is x minus 1, x1 minus x0 or x2 minus x1. They're all the same. So now I'm going to write some formulas here. Delta x, which is our distance for each one of these rectangles, is given as x1 minus x0, which is also x2 minus x1, which is also x3 minus x2, which is also x4 minus, they're all the same. But if you carefully observe, you will figure out the formula as b minus a divided by the number of rectangles in between them. That should be immediately common sense when you look at this thing. This formula is going to be used a lot. So please look at this and realize that the entire picture, entire area that you're calculating is between a and a b, and then when you subtract a and a b, you divide by the number of rectangles, and in our case that's 4, right? So for our case over here, delta x is equal to b minus a over 4 for the example above, because I only have 4 rectangles. So n is the number of rectangles. All right, great. Let's then write the area. Area is approximated by, and I'll put AL, area of the left rectangles, right? Left-hand rectangles. So what do I have? I have first rectangle, which is going to be f of x0. Guys, f of x0 is the height of the first rectangle times delta x on the bottom, plus f of x1 times delta x plus f of x2 times delta x, and finally plus f of x3 times delta x. So all I have done here is I went and multiplied every height, which is computed by plugging in x into function to get y. So y is the height. And then we have delta x as the width. So we have what we need over here. And now the next one is to actually simplify. I am going to pull delta x outside, so it's easier for us to compute this thing. So I have now, I don't want to call this fast, but I have a way to compute. And actually, that's the formula, right? Now, what's going to happen if I have 6 rectangles? Well, I'll add 2 more to this, right? So this is my, this is the way we're going to compute stuff. So let's go and compute an example immediately. How about to find, let's say f of x is equal to square root of x. We are going to go on the interval 2 to 6 using n equals 4 rectangles. All right, so I want to draw this right away because it's easier if we have the picture. I'm going to use, so 1, 2, that's 2, 3, 4, 5, 6. So 2 to 6. This is my f of x equals square root of x graph that you must know. And now I am going to use rectangles. So I have to create 4 rectangles, but we can see that if we go on each integer, I purposely did that so we are not going crazy. And now left is touching the function. So now look, we are working on the left again, but this time they are going to undershoot. Well, it depends if it's going to be overshooting or undershooting. That depends whether the function is increasing or decreasing. What is important is that the left corner is touching the function. We also have right corners touching the function, and that's going to be AR. So that's next. All right, so what's my delta x? Delta x is b minus a divided by 4. Ah, it's 1. Nice. Well, we know it's 1 because we can see 2 to 3 and then 3 to 4, and so the difference between any of these two numbers is 1. That all has to match up. Actually, the way to figure that out is better if you start with delta x equals and then go and feel where the things are. So now that I have this, I'm using the left rectangles. Maybe it will be good if you put the little arrows on those where you will be working on calculations. Those are the left sides. Observe that there is no left side for 6 because there is nothing to the right of 6. So 6 could be left. Is it confusing enough? Good. Just use your common sense a little bit. Right? So if you have the left rectangles have to be touching, right? Left corners have to be touching the function. Number 6 doesn't have a rectangle on its right, so 6 could be left. Right? So that's that. So now area is approximated by area to the left. And we know the formula is delta x times, and now we have f of the first one. So that's f of 2 plus f of 3 plus f of 4 plus f of 5. Make sure you also have number of functions to be the same as the number of rectangles, right? Because each calculation is distributing that one as delta x, and those are all independent areas of each of the rectangles. So now this is equal to, well, we don't have to write 1 anymore, so this is square root of 2 plus square root of 3 plus square root of 4 plus square root of 5. So what do we have? Well, we have 1.4 plus 1.7 plus 2 plus 2.2. If you just keep one decimal precision, and that's going to be, when you add all of that, what's 1, 2, 4, 6, 7, 3. 7.3. Now we know that the true area is bigger than 7.3 because you can see that my rectangles are below, right? Well, you know what? Same problem with right rectangles. So I'm going to draw again. 1, 2, 3, 4, 5, 6. So this is our square root of x function, our x-axis, our y-axis. And now we are going to use right rectangles at 2, 3, 4, 5, and 6. Now, right rectangle means it has to touch the right-hand side, so it's going to go this way. And as you can see, now the area will be bigger than the actual area. The title of the lecture is Approximating the Area, not Calculating Exactly. That's the next lecture. 5.2 for tomorrow, Calculating Exactly. Today we are approximating. So now what do I have? Well, first off, I'm going to point to the points that I am using in my calculation. Observe that I'm not using the first point now. I can't use the first point because there is nothing to the left of the first point, so that the first point could be the right side. So what I'm going to do here is I am going to, again, same formula for delta x works, right? Delta x is 6 minus 2 over 4 rectangles, which is 1. So area is approximated now with area of the right, and that would be 1 times, and now I have square root of 3, plus square root of 4, plus square root of 5, plus square root of 6. And that is 1.7 plus 2 plus 2.3 plus square root of 6. That's about 2.4. That's 2.45, but 2.4. So that's good enough. 2.2, yes, that's yeah, it's 2.2. You're right. So this is 8.3. We got 7.3 last time. We got 8.3 this time. So true area is in between 7.3 and 8.3. There is a way for us to calculate that exactly, but we are not going to do that now. All right, so believe it or not, that's it. Now we just need to see how to make it better, right? If you are able to do this, you are done with the mechanics of this, all right? The next is thinking a little bit of, the trade-off you have to make and other stuff. For instance, you see that the difference between these two numbers is 1 whole unit. That means 1 whole square of, right? Where the area would be. What is the exact area? Well, let's see if we can refine this. So what I'm going to do now is I'm going to draw a much bigger picture so that we can hopefully see better. So what I've done now is I increased the size of this graph to show the old stage first. And do you want left or right? Okay, fine, we'll do that one then. So, if I use the right points, you see that everything in blue is error. And that is when delta x is equal to 1. What I'm going to do now is, in red, I am going to cut each one of these rectangles in half. So I am going to introduce double amount of rectangles. So now we are going to have 8 rectangles. So the new situation is that n is equal to 8. My delta x is equal to 6 minus 2 over 8, which is 4 over 8, which is 1/2, which is okay, right? Because we need this to be 1/2. So our new delta x, right, that is everywhere on the bottom, is now 1/2. So these middle numbers, actually I don't need to write this 1/2 here, I just need to write the values. So this is now 2.5, 3.5, 4.5, 5.5, and those are the numbers in between. Now let's take a look what happened on the top. As I put the right rectangles, and as I zoom in so you can see, the new calculation does not include these parts. You see that? So doubling, or not just doubling, but introducing more rectangles eliminated some of the error. It didn't eliminate all. I still have these parts, right, that are now trapped with red, right? I have the parts that are trapped in red, and those parts are still error. So the approximated area is still bigger, but it's not going to be now 8.3. It's going to be less than 8.3 because, and it has to be, because you see that all of these blue rectangles that were error before are now eliminated from error. So now let's compute and see how much better did we do. I mean, what do we have? So 8 rectangles. That means that my area now is approximated by area to the right, which has 8 rectangles, and that's going to be, my delta x is now 1/2. Earlier we put 1 in front of parenthesis, now we put 1/2. Now inside I have square root of 2 plus square root of 2.5. That's the new guy, right? Because we have more rectangles. Plus root 3 plus root 3.5. Oh wait, no, I don't have root 2. I don't have root 2. These are right rectangles. There's no root 2. There's only 2.5 and on. Because, yeah. All right, so there's no root 2. Plus root 4 plus root 4.5 plus root 5 plus root 5.5 plus, and root 6 does have. Now you count and make sure you have 8 of these. Nice. We have 8 of these. So now what we do is we say 1/2, open parenthesis, and now we have to find square roots of all of these. We're going to round on 1 decimal, so we don't have to go anything crazy. So square root of 2.5 is about 1.6. Then we have plus 1.7. Then we have plus square root of 3.5 is going to be 1.9. Then we have plus 2. Then we have plus the square root of 4.5, which is about 2.1. Then we have plus 2.2. Then square root of 5.5, has to be close, 2.3. And then finally square root of 6 is 2.4. I mean, it's 2.4445, but well, great. So now what do I have? I have to add all of these numbers and then divide them by 2. So 1, 2, 3, 5, 7, 9, 13, 14, 15, 16, 2. If I did this correctly, and we get 8.1. 8.1 is less than 8.3, so we eliminated 0.2. That was pure error. That was pure error, all of that stuff. So 0.2 has been eliminated, and now we have a better statement that our true area is between 7.3 and 8.1. You can keep doing this. You can keep doing this on adding more and more and more rectangles. What are you doing as you are adding more rectangles? Exactly. So error is getting smaller, your result, and the answer is becoming better as you are getting more annoyed with the amount of calculations that you have to do. So what is the trade-off? The trade-off is what is the amount of calculations that can be done efficiently, right? So that we actually have the desired precision. And as I said, go ahead, use 40 rectangles. It's going to be 40 calculations, right? For a function, then you have to add them all and divide by whatever amount of delta x you get at the end. The idea is that you can keep splitting and inserting these rectangles, as many of them as you want, until you basically pass out. So now, the last part of this lecture is how do we write this, since it's so annoying and so long. How do we write this in a form that it is concise and easy to work with? We are introducing sigma notation, which is this symbol that you have seen in mathematics or walking around, being alive. So what is the meaning of this sigma? Well, sigma notation in full goes I equals, let's say, 1 to 5. I'll say counter I starts at 1, ends at 5. For the formula over here, I squared, for the formula, for this formula. So you can specify where to start, where to stop, and the formula goes inside. The sigma operates on that formula. So let's see what this looks like. If I write this out, where I starts at 1 and ends at 5, I will have to write 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared. So what the counter does, what the counter I does is replaces the I with values, integer values 1, 2, 3, 4, 5. It starts at 1, ends at 5. You can specify anything you want. I mean, whatever the problem needs. But the thing is that any numbers, any integers can go for 1 and 5. And then I will be replaced in each loop. I will be replaced with the next integer. So we are starting, as I wrote, a counter I starts at 1. So I starts with 1, and that's 1 squared because that's the formula. And then plus, because it's summation. There is also another one with a pi. If you put big pi, then it's times in between. Not worked on in, I don't know, undergraduate 400 level course will introduce pi probably. But in this case, right, we are only working with sigma, and sigma is summation, so we're adding. And then that's equal to some number over here. Summation of, let's say, ix minus 2, when I starts at 3 and ends at 6. Well, this is going to be 3x minus 2 plus 4x minus 2 plus 5x minus 2 plus 6x minus 2. Observe that my I is actually the slope of x, right? So, and then I is the counter that goes from 3 to 6, so each next term has to have the next integer, 3, 4, 5, 6. Now, yeah, you can go ahead, work out the algebra of this, add all of these things together. Right, so you gotta have 18x minus 8, right, at the end, when you add all of these terms. So that's a fancy way to write 18x, right? Minus 8. Now, why do we want this summation? Because I really don't want to write the formula for 8 rectangles, f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4 plus f of x5 plus, right? That's the speed at which you're writing. So it is much better if I go my f of x, let's say 0, plus f of x1 plus dot dot dot, because I'm lazy, through f of x, let's say 7, is just simply summation of f of x I. You see, I could be a counter, so I have, and I start I at 0 and I end it at 7. So now I can grind through all of these guys and just write them in one statement, and then later on I will just say times delta x. Now that formula says you need to add all of those numbers first, and then you will multiply by delta x at the end. This does not save any of your calculations at all. This is a convenience notation. This is because we are lazy, okay? That's it. You are learning this because you want to be lazy, because when you need to write this damn thing 8 times, right, and you have 8 terms, that's 64 terms. No, right? We want to just write one little condensed thing. If you are computing this by hand, well, you have to expand the whole thing, and when you expand the whole thing, then it goes down and you calculate each one independently, just like I calculated here. All 8 by hand, long ways. There is no way to make that shorter. That's that. So we are going to now write our formula. Oops. Formula as summation of f of xi, where I starts at some value, let's say at 0 and goes to n, and then you have times delta x, and that will be the new formula that is condensed formula for our calculation of each rectangle. So now this formula will be approximating area. Now, if you just have to be careful where you begin, right? You have to be careful where you begin. And a student once asked me, well, can you start I equals A, right? Because last time we had that A is 2, and that would definitely be f of 2 is the first one. No, you can't. Because you can't start at lowercase a, because what are you going to do if your lowercase a is 1.6? All right, that doesn't work in a summation. So we are going to see actually that this counter is actually your delta x. So it will be going from its discrete values. So it's just a counting 1, 2, 3, 4, 5, 6. You can start at 0, you can start at 1, you can start at 7. It doesn't matter where you start. So what is there tomorrow? Tomorrow we are going to take this formula and make it, improve on it, to have it calculate exact area under the curve, and we are going to define that particular formula as a Riemann integral, and we are going to call it definite integral, and then we're going to have some calculations. Make sure you don't miss tomorrow. At all costs, don't miss tomorrow. Those of you who did class preps, you are already like, oh yeah, that's tomorrow. Yeah, we'll be here at 6 a.m. I know. So I will see you all tomorrow, and we'll grind through the rest. Ciao.